Okay, now we'll be talking about geometric sequences. If you know arithmetic sequences, a lot of this should seem familiar. Okay, so onto the difference. When you have a geometric like this one below, you're multiplying each time. So this would be times 2, times 2, times 2, times 2, and times 2. As opposed to arithmetic, where you have like 1, 3, 5, 7, where you're adding something each time. Here we have a common difference, but in geometric, we have a common ratio, which here the common ratio is 2. And if this list was in reverse, it would be 32, 16, and so on. R would be 1/2, since you multiply by half each time. Okay. Now on to the first problem. The first term of a geometric sequence is 5, and the common ratio is 2. What is the fourth term of the sequence? Okay, well, obviously, we know the first term is 5, since it tells us. And the common ratio is 2, so we're going to multiply by 2 again, get 10. Multiply by 2 again, we get 20. And again, and we get 40. Okay, so we multiplied by 2, multiplied by 2, and we multiplied by 2. So our answer is 5 times 2 cubed. Okay, and notice how when we had the fourth term, we did this 3 times. That's because we did 5 times 2 to the power of 4 minus 1. We'll be seeing this concept later. Okay, on to the next one. At Adrian's awesome savings vault, the simple interest rate is 40%. If you invest $100, how much will it be worth after 25 years? Okay, so let's try to write this as a sequence like the last problem. Okay, so if it's $140 here, first term, we have to multiply by 1.4 again for the second year. So first year. For this, I just did 100 times 1.4. And for the next year, we're going to multiply by 1.4 again. So 40 times 1.4, we get 196. Multiply by 1.4 again, 274.4. And again. Okay, you're going to start to notice that this is going to take a while. We want to find the 25th term using this. So let's go back to this idea we had here. For the fourth term, we subtract 1 from it since we really multiply 3 times, not 4 times. Let's do the same thing here. Here we don't really want the 25th term, so we're going to multiply 24 times. Okay, so our first term is 140. And we want to multiply this 1.4 24 times. So our answer is going to be 140 times 1.4 to the power of 24. Check what that is real quick. It's going to be 140. Sorry. Okay. 140 times 1.4 to the power of 24. And our answer is $449,987. Amazing. You'll be rich after this. Okay. And here, this is the formula we were really using, this guys. You might see some parallels to the arithmetic sequence formula, which is a to the n equal to a to the 1 plus d times n minus 1. We have some commonalities in here. We have the same a of n. We have an a of 1 term, which is the first term. And we also share this n minus 1. Okay, now onto this problem. A geometric sequence has a first term of 1000. If the common ratio is 50, find the explicit and recursive sequence rules. Okay, this one's just for getting familiar with the formula. So let's write it out real quick. A of n is equal to a of 1 times r the power of n minus 1. Okay, so you have that the first term is 1000, so we can replace that in here. A of n is equal to 1000 times ratio to the power of n minus 1. And we're done for the explicit one. Okay, so that's half of our answer. And for the recursive. Okay, again, recursive. It's like doing that manual thing. So we're secure our braces. Give our first term, a of 1 is 1000. And what are you doing in this sequence? Well, you just multiply the previous term by 50 each time. So a of n is equal to a of n minus 1, in parentheses, times 50. And that's the recursive rule. Okay, let's do a little more challenging one now. A geometric sequence has a third term of 686. If the fifth term is 33,614, what are the explicit and recursive formulas of the sequence? Okay, formulas rules are unchainable, by the way. So a of n is equal to a of 1 times r to the power of n minus 1. And we're going to put in what we do know. Okay, so we know the third term is 686. We can write it like this. A of 3 is equal to a of 1 times some ratio we don't know yet to the power of n minus 1. And here, if we put in 3 for n, we're going to put in 3 minus 1. And we do the same thing for the fifth term. Okay, and simplify these exponents. 3 minus 1, I hope you know that that is. That's 2. 5 minus 1 is 4. And we know what a of 3 is. It's 686. And we know what a of 5 is. Okay. And now from here, this is what I would do. You can divide both of these equations to get rid of a of 1. Kind of similar to elimination, where you have system equations. You can divide these two and find the value of r. Okay, so let's do that. Divide these two. We're gonna have 686 divided by 32,614. And since this is a of 1 divided by a of 1, they cancel out. It's equal to r squared divided by r to the 4. Okay. And I will put this into a graphing calculator now. So 686 divided by 3361 equals x squared divided by x to the 4th. Okay. And we get that x is equal to 7. Okay. And you might have seen that there was a negative one. You could have tried it and you'd see it wouldn't have worked. Okay. So we get that r is equal to 7. Okay, so now we know that r is 7. We can start to substitute it back in. So 686 is equal to a of 1 times r squared, so times 49. So that means a of 1 is equal to 686 divided by 49. Calculate that real quick. 686 divided by 49 is 14. Okay, so now that we have the first term, which is 14, we can write our rules. Okay, so now we have that a of n is going to be equal to a of 1, which is 14, times r to the power of n minus 1. So 7 to the power of n minus 1. Okay, that's our explicit rule. And now for the recursive one, which is admittedly a little simpler. Okay, first term is equal to 14. And how do you get to the next one? Well, you would just multiply the previous one by 7. Okay, and now to geometric series. When you begin to replace the commas with plus signs, you're dealing with a series, as just is the case with arithmetic. To find the sum of a geometric series, use the following formula. Okay, so the sum of the first n terms is going to be equal to a1 times the quantity a. Okay, and when you begin to replace the commas with plus signs, you're dealing with a series, as is the case with arithmetic. To find the sum of a geometric series, use the following formula. Okay, so we have that the sum of the first n terms is going to be equal to a sub 1 times the quantity 1 minus r to the n, close parentheses, all divided by 1 minus r. Okay, so let's start using this formula. We can actually do this, drag it here for it to help us. Okay, find the sum of the first 4 terms of a geometric series with a first term of 2 and a common ratio of 3. Okay, so we're going to have that s of 4, that's what we're going to find. It's equal to a of 1, it's our first term, so 2, they tell us, times the quantity, 1 minus ratio to n, so we know n is 4 here, 4 here, all divided by 1 minus r, so 1 minus 3, 5 with 2. You can do this quickly with a calculator. If you don't know, 3 to the 4 is 81. Okay, we get that 80 is our sum. Okay, now to this one. Since this one's hard to remember, I'll keep dragging it along for reference. Okay, a geometric series has the first term of 10 and a sum of 163,820. If the common ratio is 2, how many terms are in the series? Okay, so S of n, we know that's total sum here. So that's 163,820. And that's equal to a of 1, which we know is 10, times 1 minus ratio, power of n, all divided by 1 minus ratio, so 1 minus 2. Okay, so we get that 163,20 equal to, okay, this turns into 1 minus 2, so that's negative 1. So really we have negative 10 times 1 minus 2 to the n. Okay, out subs with the calculator again. Okay, and we get that n is equal to 14. So there are 14 terms. Okay, and as you might have noticed, we're using decimals a lot more for these problems and calculators in general since we're dealing with powers. Often these powers, if you want to solve them manually, you're going to have to use logarithms, which is its own separate topic. Okay, so now on to infinite geometric series. Sometimes, not always, you have some that are like 1/2 plus 1/4 plus 1/8 and on forever. How would you find the sum of these? Okay, so let's just take this for comparison. What we're going to do is just make this vanish for infinite series. Okay, so now we're just going to have a of 1 divided by 1 minus r. Okay, one thing that I'm curious, the r value must be between negative 1 and 1. and we'll see why soon. Okay, find the sum of 0.5 plus 0.25 plus 0.25. Okay, let's rewrite that into a more recognizable form. This is 1/2 plus 1/4 plus 1/8, and so on. Okay, since this is an infinite geometric series with a ratio of 1/2, 1/2, use this formula. Okay, so our first term is 1/2, so let's put that in here. 1/2 divided by 1 minus the ratio, which is also 1/2. Okay, we get that 1/2 over 1/2, which is equal to just 1. So the sum of this is 1. Okay, on to the next one. Find the sum of 1 plus 2 plus 4 plus 8 plus 16. Okay, this seems geometric, right? So 2, 2, 2, 2. This would be fine to do. But if you put the dot dot dot, meaning it goes on forever, then we have a problem. Because if you keep adding these numbers to get bigger and bigger and bigger each time, you're getting to infinity. You can't use this formula. You can't do 1 minus the ratio. You'd get that 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 is all equal to -1, which doesn't make any sense. Okay. And that ties back to our ratio test. Here, the ratio was 2, and it was not in between -1 and 1. So when you're dealing with infinite geometric series, make sure your ratio is between -1 and 1.